Well, hello everyone, and thank you for joining me for another one of the Siemens online live training seminars. Today we're going to be talking about fourth axis machines, which we haven't had a chance to talk to up to yet. And specifically we're going to talk about the setup side and also the programming side. The programming in this seminar is going to be specific to ShopMill, which is our conversational interface. We will do another one of these seminars in the not so distant future that will be solely G-code based, so keep an eye out for that. But I think there's going to be a lot of good stuff from the setup as well as the programming side for you guys that are have the opportunity to get on a Siemens machine with fourth axis capability. I am your presenter, Chris Pollock, Dealer Support Specialist for Siemens. My contact information is here, and as always, I am certainly a resource available for you guys. A lot of you guys do reach out to me, and hopefully you've been getting some value from that. So certainly my contact information is here. I would say the best way to reach me would definitely be email, but if you guys are in a bind, you can always try to reach out to me on the phone as well. So I had it in the pop-up screen as well, but the next couple webinars, we are going to get into the new DXF reader. We've had a DXF reader, and I've actually done some seminars on it in the past, but now in version 4.7, it is now finally embedded in our control. So no longer do you have to run it from an external PC. You can actually bring the DXF files right to the control. So we're going to do that next. You guys will find that very, very educational. Additionally, we're going to start to go into more advanced turning content. So we're going to start to talk about machines with sub-spindles or counter spindles, and that's coming up in October as well. So hopefully you guys can make it. And just for those of you that maybe are new to these seminars, just to let you know where our primary landing page is, go to that top email address, that usasiemens.com/CNC for you. That'll direct you right to our main website. There's a link at that site to get to the webinars. All these webinars, after having been recorded, get posted in there as a library, as well as you can always see what's coming up. Or you can use the website that'll direct you right to the webinar page. Either way, you can get there pretty quickly. Additionally, always keep an eye out on our in-person training that we do at our training facility in Chicago. We have 3 different levels of operation and programming classes, from entry level, level 1, conversational ShopMill shop turn, right up through a full 5-axis course that I host. These classes are free of charge, and we look forward to you guys getting a chance to come out and work with us in person. So if you go to the site, just click on the agenda. The agenda, you can download an agenda, and additionally you can register for the next up-and-coming class. My next 5-axis class is going to be this August, so hopefully maybe I can see a few of you guys there. So this content is specific to our 828 and 840 controls. So anything we do here really should work on either control. And as we go through it, if there's something that pops out to me that is limited to one or the other, I'll bring it up. But as of now, I don't believe any of the things that we're going to talk about today can't be utilized in either of the 2 controls, certainly as long as they've been set up and the appropriate options are available. So today's webinar, we're going to look at 4-axis milling. We are going to look at 2 different variants. So we're going to talk about vertical and horizontal. I'm going to show you some neat little tricks, some utilities built into the control when you want to do like maybe multiple parts with multiple clampings. We're going to look at just traditional 4-axis programming. So you're going to get a good overview and scope of the overall process of handling a machine with a 4th axis. So there's 2 most common scenarios or configurations of machine tools in the industry today. You're going to see all kinds of different things. So I'm highlighting the 2 I would say most common or most popular. On the left, we see a traditional vertical milling machine. Whether it's a machining center or an open machine, really doesn't make much of a difference. It's still a vertical machining center. Vertical meaning the Z-axis is moving in a vertical orientation. And there you see one with a traditional 4th axis table, bolted right to the machines table. Typically used more for parts where we're actually machining on multiple sides of the part. So I'm getting a single part off the machine, but maybe I have some more complex geometries to cut. And then certainly the machine on the right is your traditional horizontal style machine. And these machines tend to have a larger type of indexer as its fourth axis. Could be full fourth axis, may just be positionable. And there you're going to start to see all sorts of different work clamping scenarios. So those will be the two scenarios, and we're going to explore both of them as we go through this webinar. So the first machine we're going to look at, and we're going to pay quite a bit of attention to it, because I would say it's probably the most common, at least in the US, is a vertical machining center style machine with an A-axis rotary table. So from the controls perspective, if you're only used to or familiar with 2 or 3 axis variations of the Siemens control, you will get a new axis. The rotary axis will be displayed below the linears. In this case, this machine happens to have an A-axis rotary. So depending on the configuration, you're going to see the axis type may change, but it's going to be displayed the same. So you're going to get the same kind of axis count and layout. Spindle is going to be the same functionality as a standard 3-axis. You just now have this additional rotary. So how is it configured and why is it called an A? So what happens is there is an industry standard as to kinematically how you're going to label a machine. So you have your X, Y, and Z linear axes, and each of those axes have an associated rotary axis that spins about around them. So the X-axis, any rotation that spins about X, the standard industry standard would be calling it an A-axis. So that's why this machine has an A-axis physically in it, because it's revolving around the X-axis. Additionally, if the rotary revolves around Y, like we're going to see a little later, it could have a B-axis designation. And then about Z, it's going to be traditionally referred to as a C. Now, it doesn't mean that a builder doesn't have to follow these rules. These are just the industry standard protocols. So that's the most common scenario and what we encourage our OEMs to follow. This way there's consistency from machine type and machine model to machine model. And even the consistency transcends control builders. So, you know, if you're on a competitive control, they should be following the same format and orientation of the machine kinematics. Now, from a machine 0 perspective, 0 is typically going to be still set in the same place. So some builders like to set it at the corner of the travel. Some will orient it in the center of some of its features, maybe the center of the rotary. So that's just knowing your machine control. But then the offsets certainly going to build from there. So we're going to talk about the offsets here. And when you get to a 4-axis machine, it tends to set up a little differently than you're used to in a standard 3-axis mill. Now, prior to getting to the offsets, there are 2 different types of rotaries I would say are the most common as far as setup or commissioning of a rotary. Type 1 would be a rotary with limited axis travel. So that would be an axis that, for any number of reasons, could be mechanical restrictions, could be that there's hosing going through the center of the rotary for clamping, but there's something that's keeping this rotary from being able to spin continuously. And that's what we would consider a limited axis travel. So in those machines, they will go to a specific value, set of degrees, set by the control, and when they get there, it will stop. In that condition, since it can't run continuously, you run into what we call unwind conditions or rewind conditions. You get to a point where you actually have to go backwards now to get back to 0. So some of them will go beyond 360. A lot of older controls, this was the only way they could set up a rotary axis. So they might let them spin up to a couple thousand degrees. But then when you got there, you had to go all the way back. So the second type of rotary, and probably the more common of this type of machine layout, is what we now call a medulo axis. And that is your type 2. And a medulo axis is a rotary axis that can spin continuously. So as it hits 360, you'll see the display will roll back over to 0, and then you could just literally hold the axis jog button as long as you want. She'll just continue to spin and spin and spin. So as long as there's no mechanical restraints or restrictions, this scenario is certainly the best scenario because I don't run into any of these unwind or rewind scenarios. The machine can immediately go right back to 0. Now, there will be different types of setup with medulo axes. We'll talk about a little bit as we get into our programming. So you do have to kind of familiarize yourself with your specific machine. So things might change slightly, but it's still going to be considered a medulo axis as long as it can continually spin. So how is this going to work? How are we going to start to set up our offsets? Well, the offsets are going to set up similar to the way I would traditionally set it up in a 3-axis machine, but now I do have a rotary axis that I can offset or adjust the 0 point. So in a scenario where I'm working on a part, it's clamped in my A-axis rotary, held by a center, and maybe I have to align it to a feature and set my 0 on some feature that maybe was previously done on the part. Now I can offset an angular value in the A-axis field. You'll see an A-axis field will pop up under the work coordinate field, and that allows me to adjust the offset angularly. Now, this is where it starts to change or differ a little bit. We're typically used to setting up to a top plane. So usually we'll set up to maybe the top of the part, and all Z will be negative into the part in a 3-axis type of machine. Well, a lot of times in this vertical with an A-axis configuration, you're actually going to set the system up so the center of the rotary is going to be 0 for Z. It additionally will be 0 for Y as well. It makes it a lot easier to manage parts where you're working on multiple sides, but you do have to start to think that, okay, I have half of the width of the part is in the plus in Z. So you do want to pay attention to that. So when it comes to Z, there's really 2 ways you can start to set the tool length offsets. Most people in the US, having come from 3-axis machines, are used to using what we call a negative offset method. And that's a scenario where each of my tools will be brought down to a set datum point, whether it's the machine's table, whether it's the top of the part, and I will set my tool length offset there. So each individual tool will have a large negative number, moving them down. That works great in a 3-axis configuration, and you can certainly use it in a 4-axis machine. But if you start to adopt a positive offset strategy, you're going to find it's actually easier to manage and handle the fact that you're working on a center of a rotary. It can be challenging to try to touch off to the top of a part that's sitting in a 4th axis, especially if it's a round part. So the positive offset method, what you're going to do is you're going to establish a gauge line. So on the image on the left, you see a little dimension of 5.39, and that's a distance from some datum point. Doesn't matter where it is. Could be a little preset or light, could be the top of your table, to the spindle face or a spindle gauge line. And that becomes a positive value. And that's the value that's going to sit in the length offset. So if you look at the little screenshot just below that image where it shows the 3/4 tool set up in our offset table, you notice it has a positive tool length offset now. So at this point, I can have all my tools set up and they're independent to my part setup. And now I just have to figure out where my gauge line point, which would be that base of the spindle, like I set up before, to the center line of the rotary is, and that becomes a negative offset in the work coordinate that I'm setting up for that rotary offset. So now as I want to change tools, I don't have to try to touch off to the rotary. I can go back to a preset point and just find the distance, or I can touch tools off externally if I had a fixture or a presetter externally. So you can do either one in the setup of a 4th axis machine. You'll just find that if you can move into the positive offsets, it's going to be a lot simpler when you're dealing with 4-axis machines. Okay, so we've established a datum at the center of our rotary, specifically in Y and in Z. We talked about touching some tools off. So what we're going to do is we're going to transition into a programming example. So in this case, I wanted to program a typical part that you would see in a 4-axis scenario. So we're going to be milling some flats, milling some grooves where we'll be running the rotary axes, maybe coming around, doing some bolt hole patterns, and then we'll do some more advanced features where we'll be wrapping some stuff around a radius. So we're going to go through a good set of steps to kind of give you a good overview of how you would start to handle or program this type of part. Okay, so first and foremost, we're going to go in and we're going to start writing some programs. We're going to get into it the same way we typically have. So we'll use our program manager key. That'll just jump us over so we can start to build some programs. We can obviously write them in the part program folder or one of our subfolders. I mean, that follows true to any of the programming you've seen through these webinars in the past. We'll have an option certainly to build our program in a couple different formats. We will be using ShopMill, but I could do everything you're seeing here can also be handled directly in G-code. And additionally, we could certainly create some subfolders. So from there, we're going to start to see some new features or functions that you may not have seen before that are start to orient or allow us to handle fourth axis a little bit cleaner. And one of the things is your clamping option. Now the clamping option you see here is at the top of your header. That may or may not be in the machine, even though it's a fourth axis machine. It is up to the OEM to turn on or commission this option. It's not a build option, but some OEMs maybe aren't aware of it or just don't support it. So you don't always see it, but if you do, it's important, because if you have the clamping option and you don't select A, if you leave it at table, then you won't see simulation about the rotary axes. So it'll only show you 3-axis simulation. So you'll be looking at it wondering why my tool's not spinning around my part or why I'm not getting any motion. So you got to make sure you select that clamping option. Then from there, we're going to come down and we're going to select how, what kind of primitive is going to define the rough stock. So you have the normal selection. But what's unique now with this clamping option is you now are allowed to orient the Z-axis. What used to be the blank or the primitive used to be oriented in Z will now orient in the rotary axis orientation. So that was always a big question. We have the cylinder. Well, how do I get the cylinder to point in the X-axis, because it's in a fourth axis? Well, before the clamping option, we couldn't. It was limited to always pointing in Z. Now that we have the clamping option, I can tip that feature around. So as we set up the cycle here in a second, you'll see how even the layout looks a little different. That's the big thing that clamping gave us. It's moving around the primitive. If you get this wrong, it's not going to have any bearing on how the part program runs in auto, but from a graphical standpoint, it won't look right. So what we have here is we have our Sinumerik machine. This is a machine I built for this webinar. This is an XYZ, so 3-axis linear, plus the additional rotary. So certainly we see the rotary here below our Z, similar to the screenshot you just saw. To give you a quick little representation of what this machine would look like, I actually set this one up with a function we call collision avoidance, really more intentionally to get a little bit more of a machine space model. So as we move a machine around, you're going to start to see our rotary is going to be spinning, and we'll be moving around this rotary axis. So we'll be able to simulate this part example and give you a little bit more of a concept of the machine motion as opposed to just seeing the standard simulation. So this is where this rotary axis, this kind of light blue cylinder, this is revolving around the X-axis. So from a programming perspective, let's start writing a part program. So I'm just going to go into the part program directory, start a new program. It'll be a ShopMill program, and I'm going to call this my 4-axis sample 1. So we give it our name, select OK. Same rules always apply: letters, numbers, and underscores, no other symbols. And now it launches. So the first option, since it's turned on in this machine, is the clamping option. So had I left it at table, this would be telling the machine, hey, I'm just working as a fixed table. So if I go to my cylinder, for argument's sake, it's pointed up in the Z orientation. Now, once we select the clamping option, my cylinder allows me to have it pointed in a Z-axis orientation, or in an X-axis orientation. So you can flip things around, and it applies to all of the primitives. So if I use a basic block, right, the HI, this always used to be called Z because it was always fixed to Z. Now it's height. So the height flips based on my clamping, right? My height is either tipped in my Z direction, or my height's going to be tipped in my X direction in this case because I have an A rotary. So that's the big thing just to get used to. You have a lot more control over your primitive for your simulation. Now in my case, we'll take a look at the part print here for a sec. I have this basic part. Now this is being machined out of square stock for this example. So this is actually 4x4 square stock. So I'm going to use the block centered option, and then I'm going to tell it that my width and my length are 4x4. So this would be if I was facing like in the lower third projection view. So my width and my length would be oriented. So my width would be in my Y. My length would actually be in my Z direction, just so you can get your head around that. And what we're going to do is we're going to set establish our 0 to be the center of the part, in this case, in X. So that's why I'm going to have 5 inches from my center line to the left, and then -5 inches from center line to the right. That's establishing this part spatially. Now, when you get to your retract planes, you do want to be careful when you're dealing with this type of setup. Because keep in mind, we're establishing the center of the part to be 0. So that means I have material up to +2 inches in the Z. So my retraction plane has to be a minimum of over 2 inches, or I'm retracting into the part. So you're going to find yourself using larger retraction values than you may normally do when you're working with these rotary axes, because you have material in the plus direction. So I gave it 5 inches for my retraction plane. That should be more than enough. Safety clearance and incremental values, so that's going to be the same definition. Just how close do I get to the surface before I start beading. Type of cutting, and my retract strategy. And a lot of times, because of the center line being 0, I may, instead of using an optimized retract, go all the way up to retract plane just to give me a little safety. Once I have the part methodized, if I want to start moving everything down, keeping it a lot closer, I certainly can. But at this point, it's always best to err on the side of safety. So I'll probably use a retract strategy all the way back to my 5-inch between my drilling moves, because I could have A-axis motion involved in those. So we accept the first page, and now we've established our workpiece blank. From here, we're now going to start to build the part program. So if we look back at our slide deck here, oops, I always get the wrong one, sorry about that. What we're going to do is the next event is to start milling some of the features. So what I want to do is I want to start with this basic slot. And the slot I like because it's a very simple slot, and a lot of times we have a tendency to always veer to having to overcomplicate things. I have to use a can cycle or everything. I got to draw some kind of shape. I got to use all the cycles in the Siemens control. Sometimes the simplest thing is the best method. So in a case like this, I just want to bring my tool over manually, feed it down onto a part to a set depth, and then spin my A-axis and cut a slot. And absolutely you can do that. Nobody says you can't. And this would be traditionally how I would see a lot of toolpaths come out of a CAD/CAM system, how they've been posting it out of CAD/CAM. So this is what we'll do. We're going to show you how to do manual tool changes. You probably haven't had a chance to see that before. And we're going to just move the machine around with some basic rapids and some feeds. So this way we can position the machine without using a given can cycle. Okay, so we will transition over and we will build this event. I got a text from somebody that said we had some audio issues. If somebody could just give me a quick enter into the chat that the audio is working, okay, that would be most appreciated. You guys have me? Yep, good. Ryan's got me, so maybe it was just a little hiccup. Okay, so let's transition over the Sinutrain, and we'll start building these events. And the big thing here is just kind of getting used to the layout where some of these new features are, because a lot of times we don't have a tendency to utilize some of these events. So what I'm going to do is I'm going to expand my horizontal keys over with my gray arrow to my right. So in Sinutrain, it's this little button on a machine control panel. A lot of times it will move over with the gray arrow that's right next to your menu select key. So you'll get used to where the layout is in your specific screen. But as we expand our horizontal keys over, we get a straight circle button. Now this is always there. So this was there on a standard 3-axis mill. There's nothing unique here as well. The only addition as we go into like the straight commands, you're going to now see a rotary axis supported, where prior to this you wouldn't have seen that rotary axis. So what can I do here? Well, we can do tool changes, which is what we're going to do first. We can just move the machine around in straight linear paths. We can do circles, arcs, helix, so there's a bunch of different commands. And we also have a machine function here. So this is an area where I might want to force a spindle command, or maybe force an additional M code, or a coolant command, or a program stop, any of these events. So a lot of times the functions that are buried in standard CAN cycles are broken out and can be found under this straight circle area. So for a tool change, just select tool. It's going to give us a simple little tool field so we can go pick it just like we normally would. I'm going to use a 3/4 inch end mill to mill our groove. if we look at our print, we have a 3/4 inch groove right here. So we're just going to bring it right to size. Let's fire up our spindle, some RPM, whatever we want to run. And the DR allows us to adjust the radius of the offset if I wanted to tweak the offset right now. Typically, you would leave this blank, but you could adjust it if you wanted to kind of cheat the offset from what was entered in the offset table. Accept the event, and now the machine's going to do a tool change, but no associated cycle with it. So from here, we can start using some simple straight commands to position the machine around. So the center line of my groove is 3 1/4 inches over in the negative, so I'm going to move her over to 3.25. I want to make sure I rapid the machine to the center line of my A, which is Y0, right? Because we set up our offset, so it would know that that's the center of the part. The Z, remember, I got 2 inches of material in the Z direction, so I'm going to want to probably come over a little bit higher, and I'm going to want to clock my rotary axis. So I'm going to position her over to A, and we'll do this as a rapid move to A of 0. Accept it. All right, so now that we've saved it, now I can come down. So I'm just going to do a simple feed move in Z, and I'm going to come down to this diameter, which happens to be a radius of 1.9. So we're going to move down to a positive 1.9. So now I'm into the part by 100 thou. And let's say we're moving at 50 inches a minute. Okay. Now it's time to spin the rotary and physically cut something. So now I can come back to my straight circle. We can enter a distance to go. So now you got to be careful with this because this may change based on how your rotary axis is set up. Our first instinct would just be, hey, let's put 360 degrees. I expect it to go all the way around. Well, one of the common ways to set up a rotary is shortest path. Well, 360 and 0 are the same position. So that potentially could not give us any motion. So if you're not sure how your machine's set, a nice simple way would be to go in and kind of drive it around a little bit and check it. So a lot of times when I walk up to a new machine and I don't quite know how the rotary has been commissioned, first I want to see, is it a modulo axis? So I'm just going to jog and just see that if you watch the display, and I'll crank it down a little bit, I'm going to see that it rolls over and keeps going to 0. Okay, so now I know it's a modulo axis. So now my question is, has this axis been set up shortest path? So if I position the axis and I move the A to 0 degrees, just to clock it, right, we get her to 0. The question is, what happens if I go 45 first? Well, she's going to move in a plus direction of 45. Okay, that's great. But what happens if I go negative 45? Is it going to go back to 0? Or is it going to use that off of 360 and still go shortest path? Now, some machines may be commissioned for shortest path but not support negatives. So these are all the little nuances you're going to know about how your specific machine was set up. But in this case, I see that the machine went the opposite direction. So it is commissioned for shortest path supporting negatives, and it will calculate out the end position based on 360 minus 45, hence I go to 315. So if I'm in a position of 0, right, so we're back at 0 degrees, and I tell the machine to go to 360, will it move? Nope, because of the way it's commissioned. So keep in mind of that. Once you kind of get your head around it, that's going to change your programming strategy a little bit. So in my case, I can't go 360. I got to break it up. As long as I break it up into 2 moves, then there'll be continuous moves. Now I will get a full groove around my part. Probably going to want to pull up off the part when I'm done. So let's just go to, say, 2.5, come off the part. And now we can start to simulate it and see if we got our basic groove. And if we're good, we should have gotten a groove. So here we're rolling around, machining our groove. Now, where it gets a little tricky in a scenario like this is, what if I want to control the direction? So now I have to play around with things a little bit. I could send her to tell her to go negative, but it doesn't necessarily mean that it's always going to go to a negative direction. So sometimes you might want to break them up. I might even break them up into 3 moves, and then I can control plus or minus if I needed to truly control the direction of that milling of the slot. In this case, it wouldn't really make any difference which way I swing it. But you can play around with that. The big thing here is just understanding that machines can be set up by builders all sorts of different ways, and it's really up to you as the user to know how it was set up and commissioned, and then apply it that way. There's nothing wrong with any of these strategies. Every builder has a little different reasoning behind why they set things up. Okay, so from here, let's go back and take a look at our next event. We machined our slot. Now we want to put some flats in it. Now there's a couple different ways to do this. We're going to keep this simple initially. So we're just going to use the basic pocketing cycle, rectangular pocket. But what we're going to do is we're going to use a staging position of the A prior to machining the next pocket. So for those of you that are already familiar with our can cycles, our pockets, there is nothing in this standard pocket that denotes the A axis. So what it's going to do is it's going to run this pocket wherever the A is positioned. So I got to make sure that I've pre-positioned the A, or know at least where it's sitting. I happen to know it's sitting at 0 because I commanded it to go there at the end of the slot, right? So then I can just jump into a pocket, and it's going to machine a pocket in my A orientation. When it's time to then do the next pocket, I merely have to add one of those straight position moves to clock my rotary, and then I just do another pocket. So to see it, let's jump on in, and let's add that function. So since I know A is sitting where I want it to be, it's sitting at 360 or sitting at 0, one and the same, right? It's a medulla axis. I can jump right into milling, right into pocket, and we can fill out a pocketing cycle. So if you look at our print here, the pocket is dead center of 0, 0. So I got a tool I want to use, some feeds and speeds. I'm not too worried. We're not going to cut this reel. Then I come in, give it my center value, tell it where the top of the pocket is. That's the top of the rough stock, so it's 2 inch. Remember, Z is center line is 0. What's the width and the length? So this one happens to be 3 by 3. So we'll give it 3 by 3. Corner radius, if I wanted to put it in, I'll just let the end mill put it in. Where do I end up? Now, sometimes when I'm dealing with working in positive directions, I actually like to use incremental values as opposed to absolute values. And believe it or not, it's a little less math in this case. Now, it's easy when everything at the top of the part's 0. But once you start to shift things off, it may be actually simpler to say, hey, I know my depth is 1/4 of an inch. So I can just tell it, 1/4 of an inch, and then it'll move down from the top datum plane, which is your Z0. Step over, depth of cut, all the rest of the stuff's the same that you're used to. So we can accept that pocket, and we should have a pocket now at the top of the part. So the next thing would be to position the rotary. So jump back to your straight circle, go back to straight, and now I can just do a quick rapid move and tell the rotary where to go. And you do want to pay attention to your positive and negative, so let's leave it at positive first. You'll see where it goes, and then we can flip it to another orientation. And since in this case it's the same pocket, just at the new orientation, I'm just going to paste it. You can get as elaborate as you want here. Repeat commands, all that kind of good stuff. Let's do a quick simulation. And now we should see 2 pockets, but you can notice the position that I put the pocket in is in a different location. So we spin around, do our thing. Come over, machine our pocket. In this case, see how it went to this front side. So that would be a positive direction. But if we look at our print, that's not where I want it, right? I want it to be in this back surface. So I now just have to go into my rotary position move, change it to -90. We do a final simulation. You can see it's going to flip that face to the opposing side. Quick little trick in simulation, if you want to speed things up, just do a Control-M. That brings the speed to max. Control-M again will bring it back down to the original feed rate I was at. But now we see the pocket's been moved. So the pocketing cycle is going to run it wherever you stage that rotary. It doesn't really care. So that's up to you. But it allows you to start using all these different can cycles and just quickly stage the rotary and do some toolpath. Do a circular pocket, do a slot, do anything you want. All the standard cycles will work on any surface as you move it around. Okay, so we've machined our 2 flats. Now if we go back and take a look at our slide deck, the next operation is to start drilling some holes. So first thing I wanted to do is show you how to drill holes that are offset to the center line of the part, or the A-axis. And you're going to start to see, now that we've set up this machine for rotary, there's some new features coming up. We do have a couple questions coming in. I will probably wait till the end to grab them, so we'll go through those at the end. It's a little tricky, but keep entering them in as they come up, and we'll handle them. Thanks, guys. So here, we're now going to see the option to select different axis strategies. So in this case, I want to have an X, Y coordinate in association with an A. Now, they're all three on the same field, but it will stage the A first, and then do the XY position. It's not going to try, obviously, drilling with the A at the same time. That's the positioning of the A for that coordinate. If your machine was not set up and it doesn't show this selection, that was an oversight by the OEM. It's only a couple machine parameters to turn this on. So I would push back to them and see if they can get the cycles to support the rotary axes you have, because it's only a couple machine parameters. And if anybody has any questions about that, please feel free to reach out to me. So in this case, we're going to drill like we normally would. So we're going to select our modal drilling cycle, and then we're going to associate it with some position locations. And at the end, these two events will give us 4 holes at 2 different A-axis orientation locations. So in Sinutrain, we can now go over to drilling. I'm just going to do a simple drilling centering cycle. Certainly, if you were really cutting this, you would do a pecking cycle or something. So I'm going to call up a tool. Those 4 holes happen to be a 1/2-inch tool, or a 1/2-inch drill. I want to drill my holes. So this is a case, again, where the incremental is handy. If I look at my depth, they're calling out a depth and a notation right here of 1 inch. So that would be 1 inch from the bottom floor of the pocket. And remember, the pocket's a 1/4 inch down. So if I just tell it -1 incremental, I'm going to handle the -1/4 inch when I go to the position screen. So it just makes it a little simpler at times when I'm dealing with these multiple planes. Okay, so my cycle is there. Now when we go to the position screen, I can select the random locations, because I have a bunch of locations kind of spread out. And now you get some new options. So typically you don't see this field at all on a standard 3-axis mill. Once it's commissioned, you now can select, do I want to do the standard XY positions? Do I want just to do an X and an A? So in this case, it's going to keep the Y wherever it's sitting. Hopefully you left it at the center of the part. And it's just going to position holes about the A-axis. That's not what we want in this scenario. We want to have offset positions in the Y, but still the ability of clocking the rotary. Now in this case, I can handle my Z-plane, my starting plane, and remember I did my depth incrementally, so it's going to be -1 inch from whatever is in the Z0 field. And in my case, I know it's 1 inch 750 down. This would have to be an absolute position, obviously. And then you just start giving the coordinates. So the location certainly came right off the part print here. The big trick here is, hey, I'm staging my A. So I'm going to say I want to drill this first hole at A0, this second hole at A0. Then I want to go to my third hole, but now we're flipping it, -90 degrees, and my fourth hole. And then I can start to move this all over the part as we go. So you accept the event, we start to simulate it, and now you're going to start to see we're starting to get our holes on our different flats. So we'll kick the speed up a little bit, and now we have 4 position drilled holes at these 4 flats. Let me zoom in a little bit. And of course, if I did the wrong direction, we'd see them flipped around the other side, but we got our 4 holes. And we can turn on our path view if we'd like to see what the tool path. So here would be where we see it rapiding and swinging over in the A prior to drilling these 2 holes. And once it moved over in the A, since the next location didn't require another move in A, then it's just going to move to that position. The A will just maintain. Typically, like anything, you wouldn't have to restate the A, but when I get to rotary axes, I like to be more redundant. If I'm just doing X and Y, a lot of times I cheat and say, well, I'm not moving in my X, I'll just give it the Y value. When I get to rotaries, I really don't want that thing in the wrong spot. So the extra 2 seconds it takes to type the A, I would do it, but it's not required. Okay, so we're moving right along. Now we got a bolt hole pattern to put in, right? So the bolt hole pattern, I'll just get my print down here. Oops, hit the wrong button. The bolt hole pattern Same scenario, but first things first, I'm going to want to make sure that I reposition my A-axis. So remember, last move or last operation I did, I actually left the A sitting at -90 degrees. And that's why it's important to kind of keep track of where the A was prior to your next move. So in this case, I'm going to, now I'll stage it over my X. That's not as required because it'll be handled in the position screen. But what is important is that I reorient my A. Now for a bolt hole pattern, that would just make the bolt hole pattern not be oriented to the other features of the part. Again, it's not as critical, but obviously if that bolt hole pattern is critically dimensioned to a feature, I'd be wrong. So that's where you want to always pay attention to where you left the A and make sure the A is in the right spot. Same thing when you get to Y-axis scenarios. I wouldn't want to leave the Y somewhere else, assuming it's going to rotate the A-axis about that. So we'll position with a straight move, load our drilling cycle, and now we'll jump into the same locations, but instead we're going to use the bolt hole pattern. Now I could have used the first one I showed you where it was the XA, but in this scenario, I just want to keep the same X. So we're just going to use the standard bolt hole pattern, and you'll see the bolt hole pattern supports the rotary as well. All right, so we'll bring the print up. We're going to do the bolt hole pattern right here, that's in that slot. So as I said, we're going to want to do a quick position move. We'll use the straight command. It's most likely going to be a rapid. The center line of my slot is -3.250 over Y0. Now the Z, obviously I want to be above, so maybe I'll go to 3 inches, 2.5. Remember the top of that part is +2 inches. So error to the safety side. And actually as you spin it up, you got more, right? Because it's a square part. So that's why you want to always be on the safer side. Now I want to clock her to A-axis of 0. Okay, so she's clocked or positioned. We set up our drilling cycle. Same scenario that you saw. I just want to make sure you use a smaller tool in this case. The depth on these holes are much shorter, so I might as well adjust that to our -250. Again, I'm still using the incremental strategy because I'll handle the 1.9 radius that this bolt hole pattern is on in the position screen. But now I'm going to use the bolt hole pattern. And bolt hole pattern typically would just be an XY scenario, but now that I have an additional rotary, there it is. And had I had multiple rotaries, by the way, I could see multiples here, depending on how the builder commissioned the machine. Okay, so define the Z starting plane. In my case, it's 1.9 up. Where is the center line? I happen to be there, but I still want to give it in the cycle. First starting position, it's going to be right there at A0. And how many holes do I want? In this case, they'll all be the same amount, the distance apart. Now, we're starting to get some bolt hole pattern. So we'll see some of our, so there's again our slot, and we'll let her run around real quick. We've been jumping over some of this stuff, so we'll let her run for a second here. She's going to go do our flat next. Machine the flat, machine the next flat, drill some holes, and there is our peripheral bolt hole pattern right around the circumference of that part. Okay, so we are almost done. But this next feature, this goes into an actual option in the control, and it's what we call cylinder surface transformation. And cylinder surface transformation is a pretty neat feature, because what it does, it allows us to take toolpath that we've created in a two-dimensional plane, so in an X and Y plane, and it literally wraps it around a cylinder. So for us to do this next feature, this wrapped profile here, I'm actually going to do it with a standard pocket cycle. But what happens is, in this case, it's instating what's called axis substitution. So any values that would normally be affecting my y-axis are now going to be transposed into a-axis motion. There's a little bit of math involved. We're going to talk about this as we go through, but that is the fundamental of the cycle. It's taking something I tell it in y and wrapping it around and inducing or outputting a-axis motion. So this is what's called cylinder surface transformation. Now, the cycle does require an option. And it's one of those options that it's not easily added in the field after the fact. And the reason being is it's not something that just gets turned on with a checkbox. I did give you the license, options license here, if you're curious about it. That's the license number at the bottom of the screen. But it does require commissioning upon the OEM side. So if it's something you don't have and you want to start to utilize or leverage, you think it might be handy for your type of work you're doing, you do want to push back to the OEM and make sure that it has been commissioned on the machine. As long as it's been previously set up, what some guys do, then you could just turn the option on once you get the option, purchase the option. But if not, it could involve certainly somebody having to come in, at minimum, them sending you a bunch of parameters you have to adjust. As well, think about this when you're buying a machine. If you're buying a new machine, it's probably one of those options that it's not a lot of money, and you may want to consider it up front, so you know it comes in properly. Okay, so there's two things you do. First thing, you got to denote or turn the option on, and we're going to show you how to get to that. That's under your transformation screen. And then you're going to tell it the diameter that the surface is being wrapped about. So in our case, we're going to wrap it about a 3.9-inch surface, I think it is. We'll look at the print here in a second. And once I've wrapped this mode, now it's modally turned on. So once the cylinder surface command is in place, anything that comes after it automatically gets wrapped around that cylinder. Now, important, you want to make sure that you previously staged the y-axis over top of the a-axis center line, because it will use the current position of the y to try to denote its wrapping. It won't always just defer to center line, because it really doesn't necessarily know where center line is. There's nothing that's telling the control physically where center line is. So if I've set it up here and I position my y, I'm okay. If you leave it off, you'll see it do it in some random location, and that's because you didn't pre-position the y. So just keep that in mind. You got to make sure that the y is dead set over the rotary axis, the A center line, prior to instating this command. Now, additionally, a little math has to happen here, because what we're doing is we're wrapping around the surface. So any linear positions or distances in y actually become the arc length. So I gave you a little formula here, and this is the basic formula for calculating what you would put in for the y distance to do a surface where I know that it's 180 degrees or 45 degrees included angle between the two A's. See, normally you know the A positions, you know your angular positions. You don't know the arc length. So the diameter is the diameter we're wrapping about. So in our case, if I look at my print real quick, we got a 1.9-inch radius, so certainly it would be twice that. And then it's going to be times pi, and it's going to be times the included angle that I want to machine. So in this case, I want 180 degrees, so it'll be 180 degrees divided by 360, gives us 0.5. So if we do the math real quick, we take our 3.8-inch diameter times 3.14159 by pi. That equals 11.9 and change. We divide that, or multiply that, shall I say, by 0.5. You get a length of 5.969021. So what does that mean? That means if I was to take this arc right on the edge and flatten it out and measure from the start to the end, it'd be just under 6 inches long. That's your arc length, and that is what would go into the pocket field. So let's go do it. Let's go set it up. And if you get this wrong, you're going to see in graphics pretty quickly, because you just start and end will be skewed. So if we jump into Sinumerik, we're going to come back over. So again, remember I said we want to make sure we pre-position, we have the machine positioned in the y-axis. Now, it was doing a bolt hole pattern, it should be, but this is one of those scenarios that if you're wrong, it's going to skew the cylinder surface transformation function. So I would say just get in the habit prior to instating this cylinder surface transformation to position it over top. So I'm going to just jump over somewhere roughly over the center line of the part, so maybe about 3 inches over Y0, rapid. We'll send her to A0, just kind of clocks everything for me. So pre-position above the feature, Now to get to the cycle, it's under Various, and it's found under the Transformation button. Jump to Cylinder Surface Transformation, and it's a matter of turning it on. Now, there can be a couple different methods commissioned. We're just going to look at the basic one right now, but there is a way to control the nature of what happens on the sides of the slot if we're trying to offset. So we're just using the first transformation of it. We give it the diameter we're wrapping about. We hit accept, and now this is a modal command. So at this point, any move you give it in Y, it's going to induce an A-axis move. You will no longer be able to command the Y and physically see the Y move. So you go over to milling. I'm just going to use the standard pocketing cycle. We can use our 3-corner gem mill. That's fine. Now, the center of the pocket, in this case, is going to be the middle of this flat. So I know the overall flat is 2 1/4. Half of it would be 1 1/8, right? And this edge is 5. So 5 inches minus 1 1/4, or 1 1/8, shall I say. 3.875 should be dead center of that flat. The Y-axis position is 0. I'm going to leave it at 0, but this again, be careful. This wouldn't move Y. This would clock the whole thing around the part. The starting position, 2 inch, right? Because I haven't machined anything there. So this is still the same. Center line is 0. Now my width, we just calculated out to be 5.9690. So I put that in the width. I give it the length of it, which in this case is 2 1/4. Corner radiuses, I'm not worried about them, so we're going to leave them at 0. If the whole thing was tipped, now this isn't the A-axis. This is an alpha angle, so this is a rotation about the center. So this would be if I just want to take a pocket and rotate it 45 degrees, not rotated about A. So that's not going to get you there. End position, we're going down to a absolute value. We can set this one to absolute and tell it 1.9. And step over, depth per pass, all the usual stuff. Now, with this type of function, like anything else, it's modal command. So if I turn it on, get in the habit of shutting it back off. So go back to Cylinder Surface Trans and turn it off. Now, if we go simulate it, we should see a wrapped feature around the end of that part. All right, so now you see there was machining. So if I got the calculation wrong, that edge, of course we got a little radius in here, but this edge to the back edge would not be 180 degrees. So, as you start to maybe fool around with the cycle, that's the beauty of simulation, you can start to change this. Maybe I had thought it was 7 inches. So now when we simulate it, you're going to see it's just kind of wrapped further around the part. Now we're going even further down, you see? So that is that linear distance, the arc length is what we calculated. The other thing that always messes guys up is, again, that Y position, right? They're going to think, oh, well, that's centering me above the Y. It's not. It's establishing the center of the pocket. It's already wrapping. The cycle's already been turned on. So, let's change this back to the 5.9, somewhere thereabouts. So let's say I gave this 3 inches, right? So what is it going to do? It's going to actually clock that pocket. So that pocket's now going to start rotating, the center of it's going to start rotating about my center line. So see how now all of a sudden it's over here? So it's the same way, if I had a feature that I wanted to put on the bottom, I would just have to calculate with my little formula that I just gave you guys what that distance is, and then I can swing that around. So that's really the trickiest part about the function, is just doing a little bit of math to convert those Y positions. So of course in ours, we're going to put it back to 0. And what's neat about this is it's a modal command. So once it's turned on, I can start to do a whole bunch of stuff here. So, let's say for argument's sake, I wanted to add an engraving cycle, right? So maybe I want to see some engraving, but I want the engraving to wrap around my part. So I can still program my engraving two-dimensionally, but now it's going to state again, all Y motion gets converted to A, so it'll wrap it around the part. Now, in this case, I'm going to have to spin 90 degrees. That's just clocking it so it goes in the Y direction. So again, that's just rotation about the center of the feature. So here, just to show you real quick, now, the only reason why I may want to restart the cylinder surface transformation is if the other feature is being wrapped around a different diameter, right? So you do have to pay attention to that because you are telling it the diameter we're wrapping about. In this case, it's the same diameter. So I can just go right into engraving, fill out the engraving cycle however I want it, and now our final part, we're getting it to be wrapped. So you get a chance to see. So there's our pocket, and now we're going to do our engraving. Now it's going to show you Y position movement, but it's really actually A-axis motion, so don't let that fool you. And we'll just turn off our path so you can kind of see the rendering of the Sinumerik operate. So you can start to get to some pretty powerful functions playing around with that cylinder surface transformation field. Okay, so last thing we're going to show you, just to kind of get your head around the tool path a little bit, is the machine space model. So I did want to jump over, cut this part, and you can see what the resulting motion would be expected to look like. And there's a little trick I'm going to show you that's happening in the slot that you also want to pay attention to. Okay, so ready to run. I'm going to put my highlight at the start of the program so it doesn't try to do a mid-program restart. We'll jump over to auto like we normally would. But now, for me to get the machine space model enabled, assuming your machine had it, you do have to go to real-time simulation, go to further views, and make sure the machine space button's on. If you don't have it, this button won't be available. Okay, so now I'm going to start the program. And first thing I want you to notice is, okay, we're milling this slot. Now, what speed is this slot being milled at? Well, I think it's being milled at 37.5, and if I put it to 100, I would expect it's being milled at 50 inches a minute, right? Well, it's not actually being milled at 50 inches per minute. It's being milled at 50 degrees per minute. So look at how much faster everything else is going, right? But that's supposed to be all the same feed rate. So if I jump back and rerun that slot, look at the feed, right? See how it's showing you degrees per minute? So this is a little less known functionality of our control that can kind of confuse you a little bit. As long as a linear axis is in motion with the rotary, the system's going to stay in inches per minute. But if I have just the rotary positioning by itself and there's no linear to associate it with, by default we have to switch the control to degrees per minute. So with that being said, pay attention to that in just radial moves, because all of a sudden you think, hey, I should have been going 50 inches a minute. The difference between 50 inches a minute and 50 degrees per minute is a lot. So don't be afraid of kicking this up. Now, the screen doesn't know that you're just doing a rotary axis move. Actually, that's the wrong move. This screen doesn't know that we're just doing a rotary axis move. So you're going to be typing a value, what you would think is inches per minute, but really it's going to be interpreted as degrees per minute. Just make sure when you go back to your next feed move, you reinstate the previous linear, because now she's going to switch back. So if we run it, and I'm just going to crank the feed down so it goes slow. I want to see in the screen though, so you see it. So see down, I'm down in it. Now I'm programming 500 degrees per minute. So if you want to do a little math based on the radius you're out there, you can figure out exactly what that feed rate would be. That would be the equivalent of 50 inches a minute. So we're going to reset this real fast. Oops, move the Z up for a second. And we can give you one better show of what this part would look like. Cut. All right. So now it goes in. Had I moved it up, it'd be a little more realistic feed rate. I crank it down a little bit so you can see it. So we do our pocket. She indexes, does our next pocket, indexes back, does our bolt hole pattern. There's our wrapping. So we can slow it down a little for you. There you get to see the machine, the overall. And this would be how I would expect the toolpath, obviously, to look. So in our simulation, we just let the tool kind of roll around the part. Obviously, when we get to the real machine kinematic, then it's going to match this motion. Finishing up our operate, retracts. Now I haven't told it anything to do with the A, so that's why the A is still sitting at this skewed orientation position. Had I wanted to then stage it to some retract position, I can handle that as part of my retract strategy. Okay, so that is kind of what we wanted to go through from a traditional vertical machining center perspective. But I do also, oh, I forgot one little thing. That's why I make these slide decks. So the one thing I did want to warn you about is there is a scenario that you can experience in simulation and simulation only that would make the simulation look skewed. So what happens is your A-axis is most not likely set up right at machine 0. Simulation doesn't know where the rotary axis is. So I can all of a sudden get these crazy skewed simulations because I got an offset in my work coordinate system that's shifting my work coordinate to the center of the rotary, but simulation thinks that the center of the rotary is at machine 0. So this scenario doesn't occur in the machine you were just looking at because I have that collision avoidance model set up. Had I not, I need to go to this machine parameter and establish where my center line of my rotary is. So the way it works is it's parameter 53220. And this is important because a lot of guys, they don't realize this, and next thing you know, their simulation is all skewed, and they're always confused. Well, why? Once I put the offset in my work coordinate, my simulation goes batty. It's because it needs to know where center line of the rotary is. So if you look at our machine parameters, so if I go into menu select and setup, and in my case, we're going to back up, go to machine data. Under axis, I want to search for 53220. And this is the machine coordinate system position. So you have 3 indexes, index 0, 1, and 2. So in these indexes, 0 is going to represent X, 1 is going to represent Y, 2 is going to represent Z. So with those 3 indexes, I can now stipulate where the center lines are. Now it's important that I get to the rotary. So right now I'm viewing the x-axis, so I want to toggle this till I view the physical rotary. And what I would do is I would plug in the distance in the y into this field. Now additionally, if you're using positive offsets, so you're shifting your gauge line in Z to center line, you're also going to want to put the same value here. That's what establishes the middle of the rotary. So if you run into this condition, this is how you address that. And this is intended for users or end users to be able to set this up. So you can be at a much lower password level and still be able to get to these fields right here. So if you have a machine that's simulating and the simulation seems skewed, the only trick here is once there's a value in this field, the work coordinate I call up has to have the center line offset already set. Okay. All right, so do a quick mic check, make sure everybody can hear me still. Has everybody been having issues with the audio, or does it seem to be okay so far? I have one colleague that was texting me. All right, good. So Jay said the audio's been working fine. Perfect. Okay, so the next step was let's take a look a little bit about a horizontal application. So the last thing I wanted to go through with you guys today is what if I have a horizontal machining center with more of like a tombstone type strategy, and I'm really just doing standard 3-axis toolpath, but I want to handle multiple clamping. So we're going to talk about that a little bit, and there's some pretty neat features in the control that you can start to use for that. So first things first, from a machine layout perspective, I'm going to still see my linear axes, but additionally, I'm going to get my rotaries. This machine that we're going to be in happens to have a programmable quill. So that is an additional linear axis that is parallel to the Z. That's called a W axis. But the bigger thing is the fact that this has a B axis rotary as opposed to the A, which we were just looking at. So what denotes it to a B? Well, if I look at a horizontal machine, my Y moves up and down, which I would initially think, hey, shouldn't that be the Z? Well, the Z is always the axis that points towards the machine's spindle. So that's why in a horizontal, Z is laid down flat. Same thing with a flatbed lathe or slant bed lathe. Why is Z horizontal and not vertical? Z is always the axis that points towards the machine's primary spindle. So with that being said, if Y is up and down, and the ISO standard for the rotary that spins around the Y is B, we have to call it a B axis. So from here, you're not going to set up the work coordinates kind of the way we did it. Here, you're going to set up your work coordinates based on a part station, not the center of the platter, typically. So what would I see? What would the fixturing look like? Most commonly, I'm going to see a scenario like this, where I have some kind of a tombstone set up, I have multiple clamping vices, and then I'm going to have some work coordinates that flip to the different sides or locations. And you're not limited to just being able to do this on a horizontal. So if you got a vertical machine like we were just talking about, and you want to set up a fixture where you can handle multiple parts, and whether it's just 0 and 180 or maybe 3 or 4 sides, this process you're about to see can be applied to a vertical machine the same way it works on a horizontal. It's just certainly much more common in a horizontal kinematic or horizontal setup. So what's going to happen here? Well, you're going to need to decide, and this will be also paralleled with part of the setup of the function, which of the workstations are going to be work coordinate 1, 2, 3, and 4, G54, 55, 56, and 57. Your X, Y, Z, those are be positions relative to your part. So you're going to come over, you're going to part probe, you're going to do the traditional setup you were used to doing on a 3-axis mill. You're going to find some edge or some center. But the difference here is now you will have a B value, and the B value will handling the position of the tombstone. And certainly, if your tombstone's skewed a little bit, you can absolutely adjust for that at the work coordinate level. That's the whole point. But the distance between each of those surfaces is going to be a full 90 degrees if it's 4-sided. Obviously, if you're doing some more compounded, or if you had 5-sided tombstone, then the angle will be different. But in a traditional 4-sided tombstone scenario, you're going to have 90 degrees between each move. So if your tombstone's out 2 degrees, well, maybe it's 92 degrees and 182 degrees. The distance included is still, again, only 90 degrees. So that's how you're really going to set it up. You're just going to know which one, which is B0, is that work coordinate 1, is B90 work coordinate 2, and then come in and set your linear axes. So what's neat with this is we've created this function that allows me to take a part that I just set up for a basic toolpath, basic single clamping job. And we have an ability of then automatically making you a new program that'll handle all of your clampings in one shot. So what we're going to do is we're going to take this part program that you see right here. It's going to be pre-programmed for us, and then I'm going to show you how to then use this multi-clamping function. And multi-clamping, there's a function under your vertical soft keys we're going to talk about here in a sec that allows me to then say, okay, well, I want to take a program. I want to now run it on 2 clampings or 4 clampings, and the system will then build a brand new result program handling not only switching the work coordinates, but optimizing your tool changes. So if it sees, okay, well, great, he's using tool 1 and he's doing 4 ops with tool 1, then goes to tool 2, instead of getting all of your tools on the first clamping and then positioning your next one and having all 4 times the number of tool change, the system will automatically say, okay, well, let's optimize the tool changes so we can keep the same number of tool changes as if I was just doing 1 clamping. And this happens all automatically. So in the end, you're going to get a chance to see we can now methodize parts on multiple sides extremely quickly from a part that was methodized for a single clamping. So we're going to get a chance to come in and create that part program. Okay, so what I've done here is I have a second machine built, and this one is horizontal kinematic. So if I was to show you, like we showed you before in the little machine space model, this machine, the Z-axis is actually moving right here horizontally, right? That's my Z. This is more like a bridge mill or a boring mill, right? Now my Y is up and down. X would certainly be back and forth of the tombstone. And then finally, my B axis is the rotation of the tombstone around. So that's the setup of this physical machine. So if I was to first take a look at our basic part program, what I would most likely have done is just written a program as if it was in a single vise. You can simulate it. You can do everything you're used to. Now, this one, since it's commissioned as a horizontal, you're going to see it's oriented a little different. It's not coming from the top. It's coming from the side because it matches the way the machine's laid out. But here, this is our basic program, right? We come in. We do some operations. Pull away. Our part program is done. Okay. So what happens if we want to handle this on multiple sides? Okay. So first things first, and this is just a rule to the function, is you do have to be working in the workpiece folder as opposed to part programs or subprograms. Or you could be in an external drive. That's okay. And the reason being is when you do this method, not only does it create a result file, but it also creates this little INI file. You get to see what that does in a second. But since part programs only supports MPF files, it won't allow an INI to be built in it. The function doesn't work there. So what will happen is if you forget and you leave your highlighted part programs and you go expanding your vertical soft keys to look for multi-clamping, you see it's grayed out. Well, it's only grayed out because where your highlight is. So that's the big trick here. Now, I usually will bring down the main program or my source program and put it in that folder. It doesn't have to be. It can be anywhere. I just like to keep them all together. So what we're going to do is we're going to take this little drilling milling example, but we're going to set it up for 4 sides of the tombstone. So I previously set up our offsets. So I set some X, Y, and Z's. That's relative to my part. My only X's are only 0 because in this machine, the center of the tombstone has been to be machine 0. And I'm just working from the middle of the blob. But there could be any number here. The big thing, the big takeaway here is obviously these positions are now the multiple sides of the tombstone. Okay. So you expand your vertical soft keys to get to the multi-clamping button. Pick it, and now first question is, how many clampings do you want? 1, 2, 5, 10. So this would obviously be dependent on your work holding. So in our case, we're going to say we want 4. And what is the first work offset? And it'll automatically go in consecutive order. So if I start at G54, the next one's going to be 55, 56, 57. And then you can pull down. You can pick any of them. And a lot of this will be predefined or pre-set up by the OEM when he first commissions this function. Now you give it the name of the program that's going to be generated. So we'll just call this drill multi for lack of something better. Type in the name, don't need any extension, say OK. And now you're going to pick what is the source program to build this resulting program. Now, it doesn't have to be one part program. So physically, you could have 3 or 4 different programs at each different stations. The system will automatically figure out where there's like tools and methodize them that way. It's pretty cool. Normally, you're probably going to be using a single part program file. So that's what we're going to do here. So I'm going to use the on all clampings function. But I could have individually picked, and then the system will go in, look at the tools. Certainly, if there's dependency of operation, and tool 1 was the first op in G54, but it's the 3rd op in 56, well, then it can't align those. But it'll figure out where that's an issue and where that's not. So you tell it the result programs. You say OK, and the system will now build you the drill multi or whatever you called it. And it did 2 things. It did that, and it also created this INI file. So the INI file is here to allow you to rapidly recreate that source file. You don't want to make any changes inside the multi because you have quadruple of all of the operations, right? So if I had one facing operation to face off this part and I want to change my 50 inches a minute, I got to do that in 4 places, right? 1, 2, 3, 4. So you saw how quick it was to make the change. So if I want to say, you know what, I need to kick up that feed rate, go to your source file, make the change here. Once you've made the change, you only have to go to the INI, open it, say okay. It'll warn you, do you want to regenerate? Yep. It's just going to build this file for you. So now if we were to open it up, take a look at our facing op. Now we see the 100-inch for everyone. So that's step one. I mean, there's rare cases where you're going to want to go and tweak this result file. Be careful with that, because once you tweak that, the source doesn't know that. So now I'm dependent on this file, and I have to edit all of them. So I've certainly roughed it all in the other way around. It makes it a lot easier. But when it's time to run it, you're going to run this program, this result file. So just go to Auto. We're going to bring up our little machine space model here. She's sitting wherever I left it. And we'll run it. And now you see we do our tool change. There's station 1. Now it's doing station 2. Now the one thing with the multi-clamp, and I'll just slow it down a little bit, is it's going to refresh, and you're not going to see the blank go in every single position. So that's why I like to turn on the wireframe. So just your show path option. You'll see the blank at station 1, but when you get to station 2, station 3, you're just going to see the wireframe. And then when we get back to station 1, it'll show you the next op, and it won't retain each op because inside of the result file, it's actually resetting up the blob or the blank every time. So that's about the only thing. And had I simulated this normal inside of the regular simulation, I would see kind of the same effect. Now I won't see the tombstone and everything there. I would just see kind of keep running over top of itself. But now we see, now it's doing all of our bolt hole pattern. And then eventually after this, it's going to get into its pocket. Now, you want to be, if you set this up, you always want to kind of establish that work offset for that station. You don't want to start flipping things around because there is a file in the back end that's managing all of this. So the way the physical setup of this function works is there's actually a custom file. We call it our cus clamp, and this is intended to be modified by the OEM or even potentially you if there's something unique we need to happen when the system moves to this clamping. See, this multi-clamp option you're seeing, this isn't just for 4-axis mill. You could use this on a 3-axis mill. In fact, that's probably where it's more commonly used. So I don't have to be rotating. I may not be rotating if there's no B-axis. If I just have 5 vices on my table, it'll methodize a part for all those 5 vices. But if I have some unique steps that I need to make sure occur during this positioning, I have to go in and add them to this clamping routine. So what will happen here is you'll find under the manufacturer folder a cus clamp command. Now, had your system not been set up for this initially, if I go in to setup and come back down until I see system data, go to my cycles folder. If I look in manufacturer or user and I don't see a custom clamp, that just means your system was never set up for it. Now, if you see a couple of them, the one that's in user or the highest one up, that's the one it's using. So the intention here is if an OEM never set anything up, he's going to go down to our standard cycle folder. He's going to take the source custom clamp, copy it into his folder, then he's going to tweak it to his specific machine setup. Now, you're the user. You get this mode. You put on some automated vices, right? And you want to add some extra functions because there's some new M code set up or whatnot. Now you can take the cus clamp file, save it in the user folder, and now when you edit this file, this is what makes everything kind of work. So in this case, this is saying at clamping number 1, I wanted to make sure that G54 is the work offset being associated with that clamping. I wanted to give it some motion to make sure that, hey, whenever I have work coordinate 1, because there's nothing in that program that says anything about the B-axis. So this is all being handled right here in this little routine. That's kind of what makes the meat of it. But this is a very handy way to start working with horizontal machines. Now, certainly, if you don't want to use the multiple clamping functions, you don't have to. You'll just have to make sure you position the B-axis in your part program to that next work side, and then you can methodize it on your own. Okay, so from there, that is the bulk of our topic. I know we went through quite a bit. It looks like we got a ton of questions here. So let's start to go through some of them, and some of them we may have gotten to already. And if there's more you guys haven't typed in, please feel free. But let's start to talk about them a little bit. So let me come up here. Bear with me a sec, and we'll read some of these questions. Oh boy, you guys have been lots of questions. Okay. All right. Can you do an incremental instead of 2 moves? This was from Dan. I would need clarity on that. It was probably content specific at the time when I was at it. I'm not sure. Martin. Okay. Oh, how do we change from absolute to incremental? This was from Dan as well. So Dan was probably referring to inside of a cycle. All right, so I'm in some event, we're in some cycle. There's spots where I potentially have an absolute or incremental toggle here. And I'm assuming that's what he's referring to. So to toggle this, you hit your select key. However, you got to pay attention to the state of your keyboard and your number locks. If your number locks is on, select becomes the number 5. If my number locks is off on my physical keyboard, now it toggles my absolute incremental. So that's the big trick there. Whenever you want to use the select button in Sinutrain, this is only in Sinutrain. On the machine, you would just hit the select button. In Sinutrain, if you need to toggle between absolute or incremental, make sure your number pad, your number locks, is not active at that point in time. All right. Is ace trace cell always calculated from A0? Well, no, actually. It's calculated from the Y position I left it at. So remember when I was doing the feature, right? And I wanted to clock it around. So Y0 is going to be at A0. But any Y offset beyond that is going to roll right around the circle. So hopefully that answers Jay's question regarding traceal. He's referring to the command traceal. Traceal is the G-code equivalent of cylinder surface transformation. So that's what we call it in the G-code side. Or is it calculated from the angle we start at? No, I believe it's calculated from the A0 orientation. On CTX machine, the traceal mode takes diameter. Does it always need the diameter on all machines? Yes, because that is the value that we're wrapping about, right? So we have to know what we're wrapping, what surface. So we have to know that diametric value. And I don't know of any way of toggling that to a radial number, but it's always a diametric value. How does traceal work on a 5-axis machine? Swing over the AB, or then traceal C, A-axis or B-axis. So the traceal function is commissioned. So part of the setup is how we want to allow it to orient about. So on my machine here, I'm going to cancel this. When I went to traceal, I had the option of 2 different transformation types. So if I go into the machine parameters, this is what's going to start to control what is the nature of traceal. They potentially could set it up so traceal could work around multiple rotaries, but it is part of the commissioning, so we would need to see. I think on the CTXs, they at least handle traceal about the primary rotary, and I think you can do it out on the secondary rotary. But that can change from builder to builder. Okay. Does the ARC need to start or end at 0? Nope. You can start it anywhere around your orientation. Can you do helicals in traceal? Yes, because you could be doing a X or Y commanded move with traceal on, and during that move, since the Y is being switched to an A-axis rotation, you would then get an XA helical. I believe that's probably what you're referring to. Just remember, once you instate traceal or cylinder surface transformation, any Y motion is going to induce an A-axis move. You can't move the Y anymore. It's staged, or whatever. Let me say whatever axis it's rotating about. In our machine, it was about the Y. Had we had the B axis one, that would be a little different, right? Okay. Can you use, well, it's actually rotating about the X, technically. Can you use the drilling cycle in Tracesil? You know, that's a good question. I've never tried it. Generally, actually, no, that's not true. I do it in G-code all the time. I don't generally do it here in ShopMill or ShopTurn, but yes, in G-code I do. Okay. And we'll, I actually did I'm pretty sure I did a ShopTurn advanced turning cycles with the Tracesil function. So Jay, I would take a look at that webinar because I do go into some of this functionality in that one as well from the turning aspect. Sounds like you probably have a CTX machine you're dealing with. Canada does Tracesil ever machine off the center of the axis? Yes, that's this question from Jay. Jay was asking, does Tracesil or cylinder surface transformation ever machine off the center of the rotation axis? That again goes back to how I stage it before I turn it on. If I have the Y stage somewhere else, it will skew that location. In fact, we could probably show that here. So let's say for argument's sake, we had positioned this to like a value of positive, 1 inch for our transformation. So now I'm shifted before I instate my cylinder surface trans. All right, so now let's catch up. So see how it got skewed? It started to drift off the part. Because again, it's using that pre-stage value of the axis we're going to be substituting with for its rotation command. And even my engraving is off. Bring up my show path, you can start to see everything. It's shifted it now. That's why it's important to pay attention to where you stage the axis you're about to substitute with, because it will skew it. Okay, in our example, I'll just put mine back to 0. All right. What else do we have here? Boom. So Jay is asking about feed groups, specifically with the fgrep function in relation to Tracesil. I would have to try this, but I do not believe fgrep will affect Tracesil. But don't quote me on that. That's something that I would have to take a look into. Generally, we use the fgrep and fgroup functionality in 5-axis toolpath with Traori. I don't think fgrep works if Traori is not on. And generally, you wouldn't use Tracesil in a scenario where you're using Traori. Okay. All right. There's a ton of questions I was trying to get through. Danny was asking, when you're doing a positioning move in the A-axis, can you do an incremental move instead of multiple absolute moves? Yes, you could have done an incremental as opposed to an absolute, and a lot of times that may be a better solution when positioning the A-axis. Martin was asking, is there a site for us to download Sinutrain? Yes, actually there's 2 ways to do it. I believe if you go to our main landing site, the CNC for You site that I showed you before, and we can just jump over it here real quick. So there's 2 CNC for You sites. There's the US site, and I'm pretty sure we have an option here where you can request a copy. And of course, I'll never be able to find it. But there is an option here. We can send you a copy. Take a look on this main CNC View page, or you can go to our German counterpart site, and that is, again, is called CNC for You, but that's our global site, and they have the Sinutrain downloads available for you right on the global website. So easiest way to find these sites, if you just do a quick global Google search for CNC for You, you're going to see one or two things. So when you look at the resulting URA, you're going to see either the word global in the website, right? Or if we work down a little bit, you'll see the US one will pop up. There's the US one, second one down. So go to the global CNC View website, and when you get there, there is an option right on the main landing page for Sinutrain downloads, and you can download an evaluation version of Sinutrain. Limitation would be that you can write programs, but you can't export or import programs to it in the demo version. Okay. Jay had a ton of questions here. I'm trying to hit the highlights. I would say, if anything, feel free to give me a call or shoot me an email, and we can dig into some of your questions in a little more detail. There were just a couple more questions here. Oh, this question was my machine doesn't have the clamp option, so how do I get it? So the clamp option does have to be set up by the OEM. There's just a couple machine parameters that have to be set. So I would say initially, if you run into this and your machine should support clamping, either reach out to myself and I can give you the MDs you can try, or reach out directly to your OEM. Another question we had here was, can I use multi-clamping with G-code? Good question, and unfortunately the answer is no. The multi-clamping routine does require ShopMill functionality to be able to generate this multi-clamping program. So you do have to use ShopMill in that scenario. Okay, so we had a ton of great questions. I think I got to most everything. Again, if I missed anything, or if you guys want to go into any more detail on some of this stuff, please feel free to reach out to me. Otherwise, thanks again for attending. Hopefully you guys got a fair amount out of it, and I look forward to seeing you guys in the future. Thanks very much. Bye-bye.